Hello, Rashid here. Today we are going to look into interconnect parasitics. We look into capacitance components and resistance components and sources of these parasitics in the case of transistor. But then we look into how transistors need to be connected to each other within a certain region, within a closer region, or within a larger region. So that's where I introduced metal layers, interconnects. And I gave an example of Intel 0.25 micron technology, which has five metals, and then vias. So now when two transistors are connecting to each other, which are not adjacent, they need to have the signal routed to the upper metals. So now we need to consider resistance and capacitance of those interconnects too. That's where will build a complete model that will be good to understand the timing impact, delay impact. Okay, so hopefully I cover both capacitance and resistance in this video. Let's get started. So um, let's look into the very simple capacitor. Um, I will intentionally try not to go into too much mathematics, but trust me, some of those mathematics, some of those equations, as I always say, those are really important to remember. You don't need to memorize them, but remember some of the key parameters that you think can impact your capacitance and resistance. So, in this example, this is a metal. So I do the 3D just to give it the length. So this metal, this is the width, and this is the height or thickness. I'm using thickness T here, and I know the metals that are due in the last video, they were not like this, but I come to those in a minute. But just assume you have a metal like this, and that is at the bottom you have the substrate, the silicon material. I remember we took that silicon material, we created added impurity P plus in it, and then we created different wells in it. But the thing is, the bottom one is connected to ground. If you remember, we were making NMOS with that. So that one is connected to ground. Now, whenever a signal travels through this metal, okay, that there, and what is this yellow thing? There, and I remember I told you there is a dielectric. Now let's assume it's silicon dioxide. Not only between gate and the channel, but dielectric is all over the place. Wherever there is no metal, there is a dielectric. It's called interlayer dielectric. And in this case, I'm just making just an assumption there's a metal going over the substrate region. And that possible, maybe there's a metal one, there is no transistor underneath, and it sees a substrate connection. In this case, you can see the bigger, the height is smaller compared to the width. So it acts like a parallel plate capacitor. Okay, this whole plate is grounded, and this portion of it, if really the bottom portion that is facing it. So ideally I should do, that's too big. Let's make it smaller. Okay, so let's align. Not on this side, but even in the inside region. So these are the lines that I'm drawing. This is should do for completeness. This is the electric field, higher potential to lower potential. Assuming a current is flowing here, so it is at a higher potential. And electric field goes from in this direction. So with the bigger width of the metal, there's a strong parallel kind of capacitance here. And again, this is a dielectric. okay, and there is a charge here, there's a charge here, so it acts like a capacitor. And in this case, we can assume that the capacitance, the usual equation for that is, and again, this is important to remember too. I think I mentioned in the transistor case as well. So this is epsilon of dielectric, which is called permittivity of dielectric. It's like the this is will be different for different materials. So for a particular material, this will be a constant thing. You change the material, this will change. So think of that. No need to worry about this special thing. TDI, this is the thickness. This is the dielectric thickness between the two plates here. Then you have W and L. You're probably thinking there is no thickness there. This is really the area that facing the bottom plate. This is, in this case, I'm assuming this is pretty small. So the main thing that is really facing is this, then under the bottom side of this metal. Hope you got that. So remember something like this. I explained this. And how this epsilon of or permittivity of dielectric is represented. Let's split this into two things. It's represented as a relative number with respect to the permittivity of free space. So just think that again. The reason I'm explaining, you don't need to memorize this, but I'm trying to make a point here, so I'm telling you that. So it's a constant, and again, it will be different. This epsilon r will be different for different materials. This thing is fixed. Okay, so this thing is 8.85 multiplied by 10 is to power minus 12 farad per meter. Now, when for different materials, and here is the point I want to make. Okay, for free space, is relative is 1 because it's really this number. So other values are, these will be the different number for different material. So for silicon dioxide, this is 3.9. So you can think of that. This is the free space we assume as a reference point, and then this higher number means by default that material will provide a higher capacitance. So silicon dioxide has 3.9, but silicon itself, not the dioxide, is 11.7. So lot more capacitance just from the material itself is coming without worrying about how close or large they are for a given thickness. Silicon has lot more. So what do we want? Do we want to have a bigger capacitance? No, we want to have a less capacitance. So silicon dioxide, that's why it's a good dielectric to be used in a silicon fabrication. Okay, so just wanted to convey that point. No need to worry about too much, but this is important. Once you pick a material, once you pick a thickness, this thing gets bigger, this thickness gets bigger, this number gets bigger, capacitance gets smaller. That's important. So, and then width gets bigger, area gets bigger, there will be more capacitance. So you need to reduce area if you want to reduce the capacitance, or you increase the thickness if you want to reduce capacitance. So remember these two things. Okay, if it was like this, life would be simple, but as we know, life is never simple. If you remember, our metal structure is a bit like this because we want to reduce the width, okay, so that we can pack more kind of metals because the transistors are very small at the bottom. If you remember previous video, again, if you haven't watched. But in this metal structure, now this height, excuse me, the height is not smaller compared to the bottom side. This thickness or height is pretty big. So that means you will have electric field coming from the side that previously we kind of ignored is no longer ignorable. So this tells you there is another component of capacitance from these side type electric field. Again, I put the same. There's a dielectric. There's yellow. The bottom is substrate, and this is the metal. But as I explained you before that, okay, I think I need to draw a few things here. So we have a metal, but there is another metal on top of it. The next metal, let's say this metal 1, there's a metal 2 there. In that case, this guy will have, now think of this. This is ground. Right? This one has a current flowing through them. So they're on a higher level, right? Then this one, if you have, there is a this component capacitance. There is from the side, and this is ground. So think of this as grounded, right? What about this guy? This has capacitance with respect to this thing too. And this one also has a capacitance, even though less than, for the same size, less than this, because it is at higher level, the thickness kind of gets more, so capacitance is less. Not only from this side, I mean this side too, this side too. You know, maybe from this side too, smaller, but no, okay. What am I doing? Okay, something like this. Some are more, some hard. Typically, we don't write these guys. Try to make things a little bit simpler. That way, there's capacitance. You understand that? Now, if you include, there is another capacitance now on the side. What happens now? Okay, should have created a. Okay, this guy comes here. Let's say there's another metal. What happens now? Okay, there is a capacitance with respect to this one too. And this guy has now maybe capacitance with respect to this. This has capacitance to ground. This has capacitance to ground. You understand that? So now you go to that picture that I had, if you remember from previous video. Relative to, so this is our channel, and I drew different metals for Intel 0.25 micron technology, and their height and their width, and it's just 2D here. So what if that happens? That's a structure. Like there's a metal 5, 3 metal 5s are going together. There's a minimum pitch, meaning the minimum distance between them. And next we have a metal 4. It's going into the screen. I'm not doing it 3D, so I hope you understand that. If I have to understand, it's going down into the screen. So then you have metal 3 together, metal 2 is here, there's nothing here. So what are you thinking? This is nice, it's okay. It's a nice picture. Should make a copy. Alright, no problem. Let's do over that. This will have capacitance. Let's start from the top. This will have capacitance. So this will have some capacitance to write to the ground. This will have capacitance, this one. This will have capacitance of this one. From this side, there will be capacitance down. This will be capacitance there. Maybe capacitance there. I already drew this, maybe capacitance there, maybe capacitance there. Right? This guy will have a capacitance to this one. I'm not drawing all the capacitance, but just to give you an idea, there are capacitance all over the place because this yellow thing is a dielectric and there's a current flowing in this metal. So this whole thing gets very messy. Now, if you think of this, I just drew channel. There is a diffusion there where the signal travels. So then there's a capacitance from that diffusion, source and drain. to the other parts, and if there are more transistors, you see how complex this can get. There's no way you can do it with hand. So what do we do then? Well, since this whole course that I'm doing initially is on the digital IC design, and what we deal with is that we write an RTL. From RTL, we generate a very large net list. Typically, the blocks that we would do from anywhere from 500,000 cells to million, and I have seen even blocks with 2 million cells in it, single block. Those cells are, think of that, a NAND, NOR. I had a videos, I think when I was talking about combinational circuits, and there I talk about, okay, what is standard cell library, and I will talk again in the physical design series. So think of that, you have 500,000, 1 million cells or 2 million cells, and can you really, with all those cells connected together, how will you calculate the parasitics, capacitance and resistance as well? So typically first we do the layout. Okay, here is just a logical connection. Even though a lot of synthesis tools these days do have some sort of estimated layout and then estimated parasitics as well. But let's talk about, we do actual layout. It's called place and routes, PNR. Sometimes it's also called automatic place and route. So the tools like Synopsys Fusion Compiler, they or previously IC Compiler, they will do a placement and a layout of the design, routing of the design. And within those tools, uh, tools need to do figure out R and C's of interconnect so that it can calculate timing. So within those are, that is not a sign of RC extraction. So this whole process of calculating resistance and capacitance for each node between all different metals is called RC extraction. So it happens within the layout tools. That may not be very accurate, but you try to converge here. But once you have a final database, you do a sign off RC extraction using Synopsys tool, for example, star RC. Star RC will run it, it will extract all resistance and capacitance nodes, even tiny bits. And then that information comes into a static timing analysis tool such as prime time in the form of a spec file, which has all those smaller components throughout the length of the metal. And then STA will bring those, will simplify the model, lump different capacitance together to come up with some sort of graph that is analyzable in timing. So that is the process that we do. You will not be manually calculating it. What you really need to understand is, okay, generally what kind of capacitance we have. If this metal 3 is this long, it will have this much capacitance. If metal 5 goes that long, it will have that much capacitance or resistance. So generally it's really good to know those numbers so that instead of doing all the time timing analysis, you can figure out yourself, okay, generally if it's a critical path, then I need to keep the cells together within that distance, because then I don't want to have a large interconnect delays. Okay, so we'll talk more about all that in physical design, but just wanted to give you an idea of how generally we do extraction in large digital designs. Okay, next is resistance. It's not much, but I think I will stop here, otherwise video will be too long. So let's leave resistance for the next video. So that's all for now. Thank you so much. See you next time. Bye.